Now, after this rather theoretical discussion on inheritance, let's give a real example. An example of the substitution principle and how it breaks things when you don't respect it and how things just work when you do expect it. So here's a simple example of a bank account. Class account. It has a balance, the bank balance, a transfer method for putting money in the account, and get bal method for reading what's in the account. And we create a new account and we put 100 euros into it. Okay? So let's now extend this definition with a new class verbose account which displays all transactions. So we will define a new method, verbose transfer. Notice class verbose account inherits from account. We have the existing methods transfer and get bal and the new method verbose transfer. Okay? This is a conservative extension because all objects of the class verbose account have not changed the methods transfer and get bal, so they still work where objects of account worked. Now let's do a further extension with an account that has fees. Let's say the transactions now, it costs money to do transactions, and each transaction has a fee and it's deducted from the transfer amount. So if you add 100 euros to account, only 95 arrives because of the fee. This class inherits from verbose account, and it defines a new method transfer which overrides the old one. So it replaces the old definition with a new definition that takes the fee into account. This is a non-conservative extension, as we will see. It does not respect the substitution principle because it breaks important invariants. Okay, so what we've done so far is we have the class account. We have defined verbose account that inherits from account, that adds the method verbose transfer, which just prints out the transactions. And we've made a further refinement with a new class account with fee that adds the method transfer, which in fact overrides, redefines the old method transfer by making transactions with fees. Okay, so we have three classes and two methods with new definitions, verbose transfer and transfer. Now let's see how both of these methods can be written. So let's first define the method verbose transfer. This one is fairly easy. In the definition of verbose transfer, we have to call transfer. And the syntax of this is self transfer A. Self is just a reference to the object, the calling object. So if I have an object OV of the class verbose transfer, I have to, inside the method verbose transfer, I have to call transfer. So I do self transfer. So it's the same definition in the same class. That's fine. So the definition of verbose transfer looks like this. I have self transfer amount and then I browse the balance. So this is how my new method verbose transfer looks like. Let's now define the new method transfer in the class account with fee. This overrides the old one. In fact, it replaces the old one. So in the new transfer method, though, this new one, we have to call the old one. So how do we do that? Since we replace the old one by the new one, if we use self, it would just be a recursive call. Somehow we have to break out of that and call the old definition. Well, this is a different kind of a link called a static link. And in Oz it's written as verbose account, which is the class of the old definition, comma, and then the name of the method. So you have to name the class in which you want to look at the old method. So that means we call the transfer method in verbose account. Okay? So with that, account with fee looks like this. The method transfer amount calls the transfer method, the old version, in verbose account, and the amount that it transfers is actually amount minus the fee. Now remember, we have account with fee. So the transfer method has been overridden, and we've used a static link to access the old definition when we make the new definition. Okay, now let's investigate what's going on how our solution works. First of all, let me show you how wonderful dynamic linking works. Here is a fragment. I have an account with fee. I transfer 100 euros into that account. That account is called A. And then I do a verbose transfer of 200. So what happens? Well, in the first transfer, of course, I'm going to transfer only 95 because of the fee. But what about the second one where I transfer 200? Which transfer method am I calling? The old one, which will transfer 200, or the new one, which will transfer 195? Observe that when verbose account was defined, the class account with fee did not even exist yet. Okay, we've defined it first account, then verbose account, and then account with fee. So now we have an account with fee, and we're doing a verbose transfer there. In fact, it's doing self of transfer. And because self is the object itself, it's going to call the new one. That means it's going to transfer 195 euros, this verbose transfer. So the self transfer inside verbose transfer is going to take the new transfer definition into account because of the self. The self is the object itself, so we use all the most recent definitions. And this is the magic of dynamic links. It means we can write programs that will work even if we extend them later. So here's a more involved explanation of the same thing. So we have here account, verbose account, and account with fee. In verbose account, we have the old definition. In account with fee, we have the new definition. In verbose account, here, we will call verbose transfer. Which transfer method we will call? Of course, it's the one inside the object OVA. So it's the old definition, and we will transfer 200. Now, in the second call here, which transfer method will we call? Well, here we have an account with fee object, so we will transfer using the new definition of transfer. It's always the transfer in the object itself, the most recent one in the complete data abstraction. Now, let me show you why account with fee is in fact a very bad definition. In fact, it's a non-conservative extension. It does not respect the substitution principle. And the reason is that it breaks invariance. In the original account, if I transfer 100 and then I do a get balance, 100 appears in the account. So I get the balance, I transfer, I get the balance again, and in the original account, the new value will be the old value plus what I transferred. But in account with fee, that is no longer true because of the fee. So I have broken the invariant. Procedures that worked with the old account, which relied on money not disappearing, these procedures will no longer work with account with fee. I have broken my program. This is in fact a very bad definition, and you should not write programs like this. So let me now summarize the two kinds of links we've seen. We've seen static and dynamic links. So the dynamic link invokes the method in the object itself, in the class of the object, and it's only known during execution because we can put many different kinds of objects here. We only know them at the execution. That's why it's called dynamic link. This is the one you should always use by default. Okay? When you're normally calling a method in an object, it should always be through dynamic link. The static link, denoted by this, we choose the method that exists in the class superclass. This class is actually known during compilation because we know superclass. That's why it's called a static link. This one is only needed for overriding. That means when you're redefining a method that existed in a previous version. That is the only occasion you need static links. So in fact, you almost never need them during normal execution. You only need them to make sure the inheritance works. But once the inheritance hierarchy is set up, you will always use dynamic links.